Okay, so we're going to continue our series of optimization problems. This is optimization problem number 6, and it says, a wall of a building is to be braced by a beam that must pass over a parallel wall 5 meters high and 2 meters from the building. Find the length of the shortest beam that can be used. So what we're doing in this question is we're trying to minimize the length of this beam under the constraint that it has to go over this wall and it has to eventually reach this wall. So we can start by identifying what it is that we're trying to do in this question. And in this question, clearly we want to minimize the length of the beam, which I'm going to call L, and then we're going to have to come up with a formula for L, so we write L equals. Now, in order to best do that, we should go back to our diagram, and we should decide what L exactly is. So I'm going to come in, I'm going to label this L as this distance, the length of this beam. And when I look at what's given in this question, I don't see a good way of coming up with a nice formula for this variable L, not with the information we have currently. Now, one way that I could do this is I could think about doing something we've done a number of times before, which is to break this length into two shorter lengths, both of which seem to fit the diagram a little better. And so let's try that, and we'll have this distance, which I'm going to call one piece of the beam, and this distance, which would then clearly make up the rest of it. And we can see that if I add those two lengths together, I'm going to get capital L. And I'm going to find these in this way. I think I'm going to call this L1. I'm going to call this L2. Well, I have a little more information now. L1 and L2 seem to fit a little bit better in the diagram. And it looks like there might be some potential to use similar triangles. We've done that a number of times before. But to show another technique, I'm going to try something a little bit different. We haven't used this one yet. And I'm going to define this triangle here, and I'm going to label this angle theta. Now clearly, this line is parallel to the ground, and that makes these two angles, this angle up here and this angle down here, the same angle, so this must also be theta. And now I can use those angles and my lengths with some trigonometry to come up with what I actually need in order to get this equation for L down here that we've got in terms of a single variable. Because I can recognize that, for example, here in this triangle, so I'll look first at this one. In this triangle, this side is the opposite side, given that this is my angle theta. This is the opposite. This is the hypotenuse, and I know that opposite of our hypotenuse is the sine of the angle. And so I can write here 5 over L1 is going to equal the sine of theta. And so that leads me to L1 equaling 5 over sine theta. And in a similar way, I know that this 2 meters here is the same 2 meters up there. That's my adjacent side to this hypotenuse. And so I can now say that 2 over L2 is going to equal the cosine of theta, which leads me to L2 equals 2 over the cosine of theta. So now I have L1 and L2 both written in terms of theta, and that solves the problem I had here of getting a formula for L in terms of a single unknown. I had the formula L equals L1 plus L2, and I can now write that as L1, which is 5 over sine theta, plus L2, which is 2 over cosine theta. So now I have a formula for the variable I'm trying to minimize in terms of a single unknown. I need to write the domain of this equation L. And I recognize that my variable here is theta. And I go back to the diagram to see what theta is allowed to be. Well, theta could get smaller and smaller and smaller as this end of the beam moves farther and farther and farther away from the wall. Theta could get smaller down to the point of 0. It could never quite get to 0 because there's always going to be this wall here, but it could get infinitely close to 0. And so I think, well, the smallest value for theta therefore has to be 0, not including 0. If I wanted to make theta bigger, I would have to move this end of the beam closer and closer to the wall. And as I do that, I could imagine having a beam which is going to get increasingly long. If I move it over to here, my beam is now going to go up something like this. And I can see that the angle here, theta, would keep getting closer and closer to 90 degrees. It would never get to 90 degrees because in order to get to 90 degrees, it would run parallel to this wall and would never actually touch this wall. But it can get as close to 90 as we want to make it. And so theta is constrained to be between 0 and pi over 2 radians. Well, now I know what my theta is. I can go ahead and try and work with this. I think 5 over sine theta and 2 over cosine theta, I know I'm going to want to take a derivative, and I think this is going to be a little bit easier to take if I rewrite these as 5 cosecant theta and 2 secant theta. Now I can go ahead and take the derivative dl d theta, and that's going to be a pretty straightforward derivative. This is going to be minus 5 cosecant theta cotangent theta. This is going to be 2 secant theta tangent theta. And I eventually need to set that equal to 0, find out where it doesn't exist, and solve it. And it's going to be easier to work with this in terms of sines and cosines, I think. So I'm going to rewrite this as negative 5 over sine theta times cotangent, which is cosine theta over sine theta. And then I'm going to say plus 2 secant, I'm going to write as 1 over cosine. And tangent, I'm going to write as sine over cosine. And now I've got everything in terms of the more familiar sines and cosines. And I could put this together a bit. I'm going to write the positive one first. So I've got here 2 sine theta over cos squared theta and minus 5 cos theta over sine squared theta. Now I need to find out where this equals 0 and where it doesn't exist. And I can see right away that the only place where this is going to fail to exist would be when cosine theta equals 0 and cosine of theta equals 0 only at pi over 2 radians, and that's not in my domain. Or when the sine of theta equals 0 and the sine of theta equals 0 at 0, and that also is not in my domain. So I can say here that dl d theta exists for all theta in my domain. So all I really have to worry about then is taking this equation and setting it equal to 0. And I can see that that's going to happen when this piece is equal to this piece. So I get 2 sine theta over cos squared theta has to equal 5 cos theta over sine squared theta. And if I multiply the sine over and the cosine over and bring the 2 to the other side, I'm going to get in the numerator of this equation sine theta cubed. The denominator of this equation cosine theta cubed. And on the other side, I'm going to be left with just 5 halves. Sine theta over cos theta, of course, is tan theta. So this is tan theta cubed equals 5 halves, which gives me that tangent of theta is the cube root of 5 halves, and that theta, therefore, must equal the inverse tangent of the cube root of 5 over 2. Now, if we had a calculator, we could solve that, but we're going to assume that we don't have a calculator. So I'm just going to have to leave that as that fairly messy thing. I don't want to have to keep rewriting it, so I think I'm just going to give it a variable name. I'm going to call this theta m, as in theta maximum, the value of theta that's going to, sorry, theta minimum, the value of theta that's going to minimize the length of my board. Now, I can look at a labeled sign chart, and I can see I want one vertical bar because I've only got one critical value. I'm going to need 2 horizontal bars. And I'm going to put in here that my critical value is when theta equals theta sub m. And here I'm interested in looking at L prime and L. Now, because I don't know what theta sub m is, it's going to be sort of hard to substitute values in. So I'm going to do the same little trick I've done a few times before now. I'm going to go back up here and I'm going to think about, okay, what happens to the length of the beam as theta gets very close to 0? Well, for this value of theta to get close to 0, as I said before, this beam would have to move out here farther and farther to an infinite distance away from the wall. And of course, as the beam moves farther and farther away, the length of the beam gets longer and longer and longer. So as theta approaches 0, the length of the beam has to be going towards infinity. Likewise, if theta goes closer and closer to 90 degrees, then the beam must get farther and farther along the ground here, getting closer and closer to the wall. It's never going to get to 90 degrees because, as we said before, if it was 90 degrees, it would be parallel to the wall and it would never reach this wall. But as it gets infinitely close to 90 degrees, I can see again that my beam is going to have to get infinitely long to eventually reach that other wall. And so because I know that the length of the beam is getting bigger as I move away from theta towards infinity, or towards 90 degrees, and the beam is getting bigger as I move away from theta going towards 0, I can of course rewrite this arrow as being decreasing coming into theta. I already know that it's horizontal there, and so I know that this is a local minimum. And because that's a local minimum, I know that L prime must have done something like that. And so now I've pretty well got everything I need. I really just need to justify my answer and write it down, which I'll do on the next page. And I can see here that L is going to have an absolute minimum when theta equals theta m, that inverse tangent of the cube root of 5 over 2. And the reason for that is because L prime is negative for all values of theta less than theta m in my domain, and L prime is greater than 0 for all values of theta bigger than theta m, again, in my domain. Finally, I can go ahead and find out what the length of the beam that we want would be. And I know that the length of the shortest beam is going to be 5 over the sine of theta m, my critical value of theta, plus 2 over the cosine of theta m. And again, because we don't have a calculator, we would just leave our final answer there. I did put this into the calculator just because I was curious to see what it would come out at. And that value comes out to approximately 9.582 meters.